Welcome. The title of today's lesson is Ellipses Day 1. It's time for us to dive into the second conic section here. And so what we'll do today is develop some of the geometry around an ellipse, and then also obviously then model it on the coordinate plane and investigate some of the algebra behind it. So let's see what I have for you here to start us out. First of all, I just pasted a little picture here. So remember kind of the situation. A plane is going to intersect our cones in some way, shape, or form. In this case, the cone gets intersected by the plane right like this. So unlike the circle, where it was kind of parallel to the ground essentially, in this case we're coming at it from an angle. And when we do that, we don't get something perfectly circular. We get something a little stretched. It's not maybe the best way to describe it, but I'm going to go with it anyway. Kind of a stretched circle, which would be, of course, our ellipse. And remember, if you'd like to see this in a more three-dimensional form, I obviously do have a model that would allow us to take a look at that. So you just let me know. Anyway, what we need to do today is sort of develop our definition of that, get that going here. And we'll do it from a very static approach initially, meaning just I pasted this ellipse onto your paper, and we're going to go ahead and try to get the definition there. But then I'll show it to you in a more dynamic way as well over the course of the lesson. So, number one, you do need a ruler to start this out. If you can grab that, that would be great. And don't blow me off here. Please get that ruler so you can kind of see this in action, and then we'll go for it. So, first and foremost, I've got a little table for you. This says distance from F1. This is going to be focus number 1. This one right over here, everybody, distance from F2. This is going to be focus number 2. So let's go ahead and get these two ready. If you would, just very, very lightly. Here's focus number 1, and here's focus number 2. Together, they make up what are called the foci, which would be the plural of focus. So if you could just kind of highlight those for me, please. And then here's how it's going to play out, everybody. This is where your ruler is going to come into play, and you're going to have to do this. Unfortunately, I'm not going to be able to be too much of a guide for you here. Well, what I'm going to ask you to do, everyone, is very simply pick a point anywhere on the ellipse. Makes no difference. I'm just going to throw one right up there and go for it. Now grab your ruler if you would, and I need you to go ahead and measure the distance from that point to the first focus, something like that. Yours is going to look quite a bit better than that, though. All right, so I need you to measure the distance, from your point to the first focus. And that is going to go right here on your paper. Put that as a number if you would. Okay, now everybody, what I need us to do is the second column. From the same point, if you could please grab your ruler and measure the distance directly. Please do it as precisely as you can. That point now to the second focus, the one right over there, please. If I didn't mention this before, which I don't think I did, go metric on this if you would. More tick marks there rather than inches. Try to go centimeters if you would. And when you have that measurement, please put it right here. All right, so you've basically taken your point and measured the distance to the first focus and measured the distance to the second focus. Now the third column, of course, kind of speaks for itself. Grab that calculator, which I know you have, of course, and add those two numbers together for me, please. Okay, so add those, whatever the distance is from here to here, and the distance is from here to here. Add them together and put that number right here, if you would. Again, I'm just doing blanks. You've got to earn your keep here and fill in those with numbers. Now, I won't make you do this a ton, but we've got to verify a couple things. So, after you have that, and if you don't have that, by the way, pause until you do. After you have that, what I need us to do, guys, is go back and pick a second point anywhere you'd like on the ellipse. I'm just going to go right down here, just try to vary it up a little bit. So directly on that ellipse, if you would, pick another point. And everyone, I need you to repeat the process. Grab that ruler, and I need you to measure the distance to the first focus, right in there. Measure that perfectly. And then if you would, measure that distance to the second focus. So it would look something like that with my dotted lines there, of course. But you are going to get measurements. So one more time. From that second point that you picked just totally randomly, didn't have any bearing whatsoever, no rhyme or reason, but I need you to go ahead and measure the distance to the first focus and measure the distance to the second focus. Put those two numbers right here if you would, please. And you know obviously what to do with those two numbers. That third column speaks for itself. Take those two numbers if you would, add them together, and figure out what that is right there. Now, first and foremost, we can probably start to draw some conclusions with this so we don't belabor the point. But what did you notice about your two sums right here? When you added those distances together from the point to the two foci, what did you notice about the sum? Should be the same, should be. If I can impose on you one more time, pick a point anywhere you'd like. Let's go somewhere totally different. Again, theoretically, I could do this again and again and again, but I'll narrow it down a little bit here. So here's what I'm thinking. One more time, third point, if you would. Find that point on the ellipse and go all the way to the first focus, or at least that's how I drew it, all the way to the first focus. And please measure that distance, whatever that may be. Excellent. Now, if you would, please, measure that distance right to the second focus. So something like that would do for me. And please go ahead and put that number right there. So measure the two distances, if you would. And you obviously know what's coming. Add those two together. And the sum. And what did you notice one more time? And again, if I'm a little ahead of you, pause me, do what you need to do, of course. But in this particular case, it should be this distance and this distance added together should be the exact same number, no matter where we are on the ellipse. And I hope you see that. You don't have to do this on your paper, but if I picked a point at random, anywhere at all, measured the distance to one focus, measure the distance to the second focus, and I add those two distances together, it's constant. Now, I'm not entirely sure, my memory is not what it used to be, but I've done this in years past with classes, and I think that the sum for the one that I pasted on your paper is about 10 centimeters. Again, you can maybe verify that or refute that one way or the other. It doesn't matter, but the sums should be the same, whatever it is. Okay, that is absolutely outstanding. So, we're ready for our definition. And so remember, you are responsible for all four of these definitions. And remember, they all start out the same. So let's get it in there. Set of all points in a plane. And then kind of a dot, dot, dot from there. Remember, we had one for a circle. I had a nice definition on that, something that you probably knew intuitively. This one obviously took a little investigating and exploring, but I think we pulled it off. So here we go. It's the set of all points in a plane where the sum of the distances, and that's what we did. So you did two distances and then added them together. And those distances go from two given points. So let's get that in there. So from two given points, and we'll talk a lot about those two given points, by the way. They're what are called the foci. So notice they're not on the ellipse, but their position generates the shape of the ellipse. And so let me just make sure I have this correct for you. The set of all points in a plane where the sum of the distances from two given points, those foci, and that sum is constant. And that is exactly what you saw right here. No matter how many times I would have made you do this, you would have found that if you added those two distances together, it's always going to be the same. Hope you saw that initially. If you didn't, please check in with me, because it should have been pretty ideal. That looks great. I'm going to bring up my program in just a second here and kind of just show it to you from a more dynamic standpoint. But I hope that you were able to kind of pull off the measurements and pull off the definition from what we saw. Good conclusion to be drawn there. All righty. Well, guys, drop the pencil for just a sec, and let me see if I can bring this up. Here we go. And so I have this program that will sort of generate this. Now, take a look, everybody. Here, I'm going to have one focus and a second focus right here. And notice I'm going to have one distance to a point and a second distance to the point. And look over here, everybody, if you would. There are my two distances. Point to the first focus, point to the second focus. Now, this is just coincidence, but it looks like we have that 10 popping up again. I could change that. It just does a default of 10. But basically, watch the sum, guys. The sum is not going to say it's not going to change. It's going to stay constant. These distances are going to change, but when we add them together, the sum is going to stay the same. And watch the shape that emerges when I take a look at all the points in that plane. Ready? Here we go. So I hit that, and look at generate. See, notice the distances over here. Very, very cool. Watch those. They're all changing, but look at the sum, guys. The sum is staying the same. And do you see the shape that emerges when this happens? As you follow it right there, we get a perfect ellipse. Again, I'll probably get fired for saying it, but kind of like a stretched circle. That looks great. I'm going to see if I can grab this and maybe bring it in a little bit. Look what happens when I kind of change the position of the foci. Still works. You know, these distances stay the same, but change, but the sum stays the same. And look, I can just kind of change the nature of the ellipse, make it more circular, make it more stretched. We'll talk about that piece. And it's all based on the position of those two foci. Wow, that looks very, very cool. All right, so I hope our definition makes sense. I hope you're seeing that piece. If you'd like me to bring this up and show you independently, I'm happy to do that, but yeah, it's kind of cool to see. All right, I'm going to reset this. Maybe we'll come back to it at some point, but let me bring back my other screen, and let's go get the next piece. So we've got our definition, as I said, which you are definitely responsible for. And now it's time to fill in all the little geometrical aspects of this. So a lot of little labeling that's going to go into this. It is the one benefit of having a notes worksheet, by the way. We get to play a little fill in the blank and then kind of draw with the one that I've had rather than you having to do it just on a notes or just, in your notebook. So let's go get them. There's no time like the present. Bunch of distances we've got to take care of here. So I'm going to sort of connect some things. Those three, let's get them going. So here we go, guys. Some things to label in our ellipse. The distance from the center of the ellipse to a vertex is labeled as, and you're going to see our letters start to come out. Our first letter, everybody, is going to be A. So let's get this going. First and foremost, I'm going to have to go back and forth. So here's my ellipse. Everyone here, of course, is the center right here. One vertex would be right here. In fact, if you get a chance, can you just write the word vertex right there? And then a second vertex right over here. All right, so the plural, by the way, would be vertices. So two vertices, and what we're looking for at this stage is the A value. So when you hear A, you're going to think to yourself, center to a vertex. There it is right there, guys. Label that in if you would. From center to a vertex is going to be called our A value. Hope that makes pretty good sense. All right, so two vertices, one over here and one over here. Okay, good. A is now taken care of. Now, the next piece. Let's read the distance from the center of the ellipse to a covertex. So the vertex is sort of the longer part, and the covertex will be the shorter part, for lack of a better description there. We went A from center to vertex, and guys, we're going to go B from center to covertex. So let me jump on back. And so if you get an opportunity, probably intuitively knew that this was going to be what we will call a covertex. And this one up here again, same covertex. All right, so kind of think of the stretched part of the ellipse, again a stretched circle for lack of a better description. The stretched part goes to the vertices, one in this case to the left and one to the right. And in here, covertex and covertex. And what did I say on that? B. So let's go ahead and get B going from there to there. There you go. That distance from center to covertex is B. All right, nicely done so far. We've got those two pieces in, two vertices, two covertices. And so when you hear vertex, just start thinking about A. When you hear covertex, just start thinking about B, and it's the center to each of those. And the last one, center to a focus. And of course, is labeled as C. So two foci. Let's go ahead and label that C value. And everyone, it goes from center to focus. So right there to there. That looks very nice. So you can see that the focus is inside the ellipse. So A is always going to be bigger than C in an ellipse. And that's sort of the relationship right there that we've developed. Okay, this is looking great. I have my A, my B, and my C. Again, a little word association there. When I hear the letter A talking about ellipses, I'm at least thinking center to vertex. B, center to covertex. C, center to a focus. All right, let's go ahead and get these, well, actually really these four go together. A couple other things that have some names. So the line segment connecting the two vertices is what is called the major axis, sort of the longer axis. So it's got a more prominent name there. And I would love for you to fill this in. What's the length of the major axis? So that would be vertex to vertex. So it is a line segment. Let's go ahead and bring that up here. Vertex to vertex. How long is that major axis right there? And again, in this case, I'm not going to put it in. I don't want this to get too convoluted in here. But I hope everyone is comfortable with the fact that this is the major axis, the longer line segment inside the ellipse. And I hope everyone agrees that it's A and another A. So the length of the major, you're going to have to know this piece as well, is 2A. Excellent. So you saw that it's kind of like a line of symmetry, so to speak. And it connects the vertex to vertex. Nice. Now, if we called that the major, you can probably guess this one. The line segment connecting the two co-vertices, so that would be the smaller one, always the smaller, no matter how we orient our ellipse. The smaller one is going to be the minor. And so we'll go ahead and see this in just a second. But again, without me putting it inside there, you will have to know this piece. So just one more time as a review, because a lot to process here. The major, guys, is vertex to vertex. The minor is covertex to covertex, so the smaller of the two symmetry lines inside the ellipse. Okay, good. Did you figure out the length on that covertex to covertex line? The minor should be 2B. So you will see some problems that ask you or really give you information about the major axis or the minor axis. As soon as I hear the word major axis, I am thinking 2A. And as soon as I hear the minor axis, I am thinking 2B. Okay, very nice. Again, relatively painless, just filling in blanks there rather than having to write all that out. Let's go get our next piece. We need the ruler again. This is a great one. There is a great relationship connecting A, B, and C, which we'll get to momentarily. I need you to do just one more piece of measuring for me. So let's read the investigation. It says, there is a relationship between the A, B, and C values. And it says, measure the distance from the center to a vertex. All right, let's do that. So everyone, if you would, grab that ruler, and in here, can you measure from center to a vertex, from there to there? That would be A, of course, from here to here. So measure what is A on this particular ellipse that I gave you. Okay, so grab that ruler, measure A. Now, what I need us to do is keep that number in the back of your mind and then do a second measurement. It says, watch this one, this is cool. Now, measure the distance from a focus to a covertex. So, focus to a covertex. I'll tell you where I'll have you do it. That'll be from here, here's the focus, to a covertex right up here. Measure that length right there, from there to there. Think of a segment connecting those two and what would be its length. And did you notice something? Did you notice it's equal to A? It's equal to center to vertex? Kind of neat. And that's always the case. So from focus to covertex is also A. It's the same exact distance as the center to a vertex. So watch this, everybody. Let's stay on this screen for just a moment. Everyone, if you would, please draw that in as the A. And then, guys, let's get a couple more things going here. Look at this. I put B. I'm going to do it from here to here. There's B, of course, center to covertex. And everybody, do you see this? There's C. How does that look? So I just threw my B and C in like I normally would there. center to covertex is B, center to focus is C, and I figured out that this little hypotenuse of a right triangle, dare I say it, that's A. And guys, what nice theorem represents three sides in a right triangle? Notice it's a little skewed in this case, but it's going to be this squared plus this squared equals that squared. So our labeling is a little off from the Pythagorean theorem, but it is the relationship at hand connecting A, B, and C. Here's how you typically see it, everybody. We usually put it in terms of C. So what you saw is B squared plus C squared equals A squared, but again, typically you write it in terms of C, or at least I do. And so it's A squared minus B squared equals C squared. That's great. Look at that. And again, if you're not sure about that, here's what I have. Again, typically you write it in terms of C. So C squared is A squared minus the B squared. Good. Keep that in mind. You're going to need that one. That one comes up a ton. All right, there's the geometry. That's great. Look at that. A lot of geometry, a lot of time to develop it, but I think that's good stuff because now we transition and we go get the algebra. So it is time to go ahead and start modeling an ellipse on the coordinate plane. So what we want to do is find an equation that will represent the infinite number of points making an elliptical pattern on the coordinate plane. Now there are only two types of ellipses that we're going to see on the coordinate plane. That's the good news. One is going to be stretched horizontally. Notice I just kind of pasted a couple pictures in here. So horizontal ellipse, one stretched horizontally and the other stretched vertically. We will not see any stretched in any type of diagonal form. You really kind of need some trigonometry to go with that one. So this is good, horizontal and vertical. Now one thing to note, and we'll do all of our remaining conics this way, when we begin modeling, at least when we begin the modeling on the coordinate plane, we will place the center at the origin. Okay, so does everyone see that here? Center right at the origin, center right at the origin. On the next notes worksheet, we do take the center off the origin. Okay, now I made the analogy that an ellipse is sort of like a stretched circle. And so you'll see this as we go through the process. The equation's going to look different than the equation for a circle, but it actually is very similar in nature. It just has a slightly different form. So let's get that form for you here. Here we go. So two fractions, a plus in the middle equals 1. Get that going if you would. So this is going to be what's called our standard form. And let's underline a couple things. So we're going to see the general form come up on the next notes worksheet. But for right now, standard, horizontal, and center at the origin. And here's what it's going to look like. So we want to model the infinite number of x's and y's on the coordinate plane. It turns out to be an x squared and a y squared. Again, similar to a circle. A and B are embedded in the model. And so the larger number in an ellipse is always going to be A. If it's under the x, then you know it's stretched horizontally. Smaller number is always going to be the B in an ellipse. And if that's under the y, again, that means that it's stretched horizontally. All right, and that's it. Good. Now let's go get the standard form of the vertical, and then we'll start to put this together a little bit. So bear with it for just a touch longer. Two fractions, everybody. And set to 1. So to the standard form, you'll see this for the hyperbola as well, by the way. And here's what I'm thinking on this. Let's go ahead and, it really doesn't matter what order we put this in, so I'll try to avoid some confusion if possible here. But basically, if the larger number is under the y, then it's stretched vertically. That's how we know. Because remember, guys, this is addition, and let's be clear on this one piece. This is addition right here. When I add two things together, does the order matter in which I place them? No, absolutely not. So theoretically, this could have been out in front, this could have been behind. So the only way to tell which way it is stretched is by the numbers down below. And so here's the deal, guys. Larger number under the x, stretched horizontally. Larger number under the y, stretched vertically. That's how we'll know. Okay, let's go for it. Couple things, obviously, with that model. We already put this on the front side, but let's go ahead and get it one more time. A, as I said, is already embedded in the equation. We did the geometry part on the front. So A is the distance from center to a vertex. B, of course, represents the distance from the center to a covertex. And of course, the x and y's represents really any point on the ellipse, the infinite number of points that make up the ellipse. So any point on the ellipse. And remember the premise, guys. Remember the sort of the marriage between algebra and geometry. The idea is if I was to plug in the infinite number of x's and y's that make this equation true and plot those on the coordinate plane, it would form a perfect ellipse. Okay, good. Let's go just try a couple examples, see if we can put it together. So 1, 2, and 3 sort of speaks for itself. So nice and easy. First and foremost, before we even dive into this, everyone put a little X right on the origin. So our center of the ellipse is going to be right at the origin. Now, again, this forms an ellipse on the coordinate plane. Love to sketch it out here and get some of the details. So let's start with letter A. Is the ellipse stretched horizontally or vertically? Now remember, just be very clear. Because it's the addition of the two fractions, the order in which they're placed does not matter. So just because the x comes first here, just because I wrote it that way, doesn't necessarily mean it's stretched horizontally. It could, but it doesn't necessarily mean. How do I know which way it's stretched? It's by the numbers underneath the variables. And in this case, if the larger number, and here's the larger number, is under the y, larger number under the y, it's going to be stretched vertically. That's our case. So start with that piece, and then as a result, bigger number is a. So in this case, I kept the numbers easy for you. That's going to be your a squared. That's going to be your b squared. So let's go ahead and get them. We're going to do a lot of counting with this. It seems kind of elementary, but it's a good way to pull this off for the most part. So letter B, what are the locations of the vertices? As soon as I hear the word vertices, I'm thinking A, and I hope everybody is in agreement that A is 5 units, because a squared is 25. And here would be the question, everybody. From our center, do we want to go left and right to our vertices, so horizontal, or do we want to go up and down to our vertices? And remember, of course, the vertices are in the direction of the stretch. So if we said it's stretched vertically, then we're going to our vertices vertically. And so what this means, and let's put this right here, up and down. So we're just going to go up 5 units from our center and down 5 units from our center. So let's do it, everyone. 1, 2, 3, 4, 5. Put a point. 1, 2, 3, 4, 5. Put a point. So up and down 5 units. And if you want to go ahead and write those vertices, I would encourage that. So 0, 5, and 0, negative 5. Beautiful. Okay, good. Had a little stray mark there. Let's get rid of that. So vertices taken care of. That would be this one. Done. Now, guys, let's go get the co's. So the co-vertices here. What are those locations? Well, as soon as I hear the word co-vertices, I'm thinking B. And again, B is part of the equation there. There it is. There's B squared. So B is 3. And we always go to the co-vertices from the center. The question, of course, becomes, do I want to go up and down, or do I want to go left and right? And I think it's fairly obvious, since I went up and down for the vertices, that I do want to go in the other directions for the co-vertices. So we're going to go right 3, put a point, left 3, put a point, and there are your co-vertices. So we went left and right for the co-vertices, just the other direction. And I'm assuming you can all give me a couple ordered pairs there. So how about 3, 0, negative 3, 0? And again, however you want to represent that, that's fine by me. Now we'll sketch this in just a second, but let's get the foci in there as well. And notice, here's the deal. Look at that equation. Is C in this equation at all? Absolutely not. But do I have a way to use A and B in order to get C, which will give me the location of the foci? Yes. And so here's where it comes into play. You will probably be using this, just about every problem with an ellipse. There's the relationship that we developed on the front side. C squared is A squared minus B squared. And so everybody, let's go ahead and just do 25 minus 9. Nice and easy, isn't it? Because A squared and B squared are those numbers. So I'm getting C squared equals 16. And C is officially, I'm going to put the plus or minus in just because both directions. You could just write C as 4 if you really want to, but I'm going to undo the square and just think of it as 4 one direction and 4 the other direction. That looks great. Now the question, of course, becomes, once we have C, which direction are we going to go? Actually, let me wait on the ordered pairs for just a second. So what would be your instinct here? Do we want to go up and down from the center or left and right from the center in order to place our foci? And the answer, of course, would be up and down. So put that in there for me if you would. So we're going to go up 4 from the center, always the direction of the vertices. The foci are on the major axis, and major is connecting the vertices. So here we go, 1, 2, 3, 4. Let's put a little X right there, because again, it's not a point on the ellipse, but it generates the shape of the ellipse. So 1, 2, 3, 4. How about right there? Okay, so that would be at 0, 4 and 0, negative 4. Hope everyone's cool with that piece. Alrighty, here we go. It does say to sketch. Now I'm going to butcher this thing, but please try to do a better job than I do. But basically we've got our ellipse, kind of stretched circle. Oh goodness. I'm going to try to go nice and slow here. Let's see. Ooh, so far not too bad. I've drawn worse, that's for sure. All right, not too shabby if I do say so myself. All right, so something along those lines, good sketch. And that looks great. Humor me if you would. Pick any point on the ellipse. I'm just going to pick one right here at random. And do me a favor, draw just 2 very, very light, barely can see them. Very light dotted lines going to the foci. If I made you grab your ruler, measure those 2 distances, and then add them together, would that be the same anywhere on the ellipse? And the answer is yes. So again, if I picked any point on the ellipse, measured the distance from one to one focus and then to the other focus, add those 2 distances together, it's constant. Cool. Alrighty. Well, let's go get examples 2 and 3 and round this out. Example 2. Find an equation of the ellipse having one focus at 2, 0 and a vertex at 3, 0. Sounds good to me. So I'm going to tell you all through this unit, be visual. Be visual. So center for right now, and I should have written it here. Again, in future lessons, if I don't write it, this would be an issue. But we're going to assume center at the origin. And if you really need to, write in there center at the origin. For right now, it's just sort of taken for granted. But center at the origin, and then a focus right here at 2, 0, and then a vertex right here at 3, 0. Okay. Hey, well, everyone, if you would, give me A equals, give me B equals, and give me C equals. I would argue that we can get 2 out of those 3 pretty quickly. So what do we have? Well, center to focus looks like it's exactly 2 units. From here to here, 2 units, C is 2. Okay. Center to vertex, from here to here, looks like it's 3. So A is 3. Can we get B? Of course we can. And in reality, actually, we only really need B squared because we're writing our model. But I'm going to go ahead and find B, put it in. But really, it's just B squared we're after. So I'm going to have to work over here. So c squared equals a squared minus b squared. I have c squared, which is 4. I have a squared, which is 9, minus b squared. Now you'll have to excuse me here because I'm running out of a touch of room, but I'm hoping everyone's okay. I like making that b squared positive. I'm going to bring that over to the other side, make it positive, and then maybe I'm going to subtract the 4. So if you don't see this, please let me know. But I'm hoping you see b squared equals 5, which is, as a matter of fact, what we're going to need. If you want to write b equals square root of 5, that's fine. But again, that's sort of above and beyond right here because we don't really need b, we need b squared. But regardless, we've got them. So I just use this nice equation right here. Shouldn't scare us too much. Hey guys, if you would, let's go ahead, 2 fractions with a plus set to 1. And again, doesn't matter the order. I know a lot of students kind of like having the stretch out in front, but it doesn't matter. So I'm going to do a squared right here. So 3 squared is 9. B squared we already determined was 5. And just remember, the larger number goes with the stretch. I'm hoping you all agree that this was horizontally stretched because, again, center to vertex is horizontal, and that shows our stretch. So if the larger number is 9 and it's horizontal, the x squared goes above the 9. And then the y squared with the non-stretch over the 5, the smaller number. And there you have it. So I told you you'd be using this equation quite a bit. And there it is. We had a, we had c, and we needed b squared. And we got it. All right. Just be careful with make sure the numbers match up with the letters. Horizontal stretch, larger number under the x. Good. Last one. Example 3. Find the position of the foci of an ellipse with the equation. Now this is where it comes into play because we've been writing our equations nicely like this, and this is the standard form. But if we sort of wrote it in a slightly different way, like this, does everyone see how close this is to the equation of a circle? The only major difference, everybody, is between this and the equation of a circle is the circle would have just 2 of the same numbers out in front. This might be just an x squared and a y squared. But here we have an x squared and a 9y squared. By putting that number in front of the y squared here, what it does, and again, this is really poor form on my part, but I like it. It stretches the circle, and it makes it more elliptical. So that's the key. It is very, very similar to the equation of a circle, but just by putting that number out in front, that's what makes the stretch. But really, the characteristics come from it seeing it set to 1. And so that's what I'm going to do, guys. I'm going to divide by 9 because I want to set this to 1. So 9, 9, and let's play this out. So this is a common denominator, everyone. So I'm going to have x squared over 9 and then the 9y squared over 9. And I'm going to just do it right here. So x squared over 9. And then 9 over 9, everybody, is really just reduces to 1 over 1. So I'm hoping you all see that that would be over 1 equals 1. So I like this problem because you can see the connection. That's, to me, the big thing. It's very, very similar to the equation of a circle. All right. Find the position of the foci. And this looks good. Let's just go ahead and write A, B, and C. It's all going to come down to those big 3, everybody. A looks to be 3, larger number, of course. So a squared is 9. There it is. A squared is 9, so A is 3. B squared is 1, so B is also 1. Could I go ahead and get the C value? Absolutely. So let's go ahead and get that, and then we'll talk about where this guy is. Where? So C squared is A squared minus B squared. C squared equals 9 minus 1. Look how nice that is. C squared equals 8. So C is equal to square root of 8. If it's okay with you, I'm going to kind of shoot for the stars here, maybe reduce square root of 8. If you put square root of 8, that's not a big deal. I'm going to go to root 2, though, because that is square root of 8, more simplified. Good. But remember, it's good to get the C value. That's a distance. Notice what the problem asks, everybody. Position of the foci. So what I want, everybody, and here's going to be our final answer over here, I want the 2 ordered pairs for the foci. Okay, so let's ask the question. We're coming off the center, which is at the origin, and am I going to go left and right to the foci or up and down to the foci? And the answer, if you look at the equation, look at the stretch, it's a horizontal stretch, bigger number under the x, so it's horizontally stretched, so we're going to go left and right, and if I go left and right on the coordinate plane, it's the x coordinate that changes. We're going to talk a lot about that. And so these are going to be your 2. And there we go. Let's box that up so we know that that's really what we were looking for, that final answer. And same with this one over here, write the equation. There we go. Whew, a lot of great stuff right there. So some amazing geometry that comes into play with these, and just starting the algebra. Very nice introduction to it. Well, I'll stop right there, everyone. You just let me know if you have questions along the way, but get a good jump on this if you can. The algebra does get a little heavier, and then we'll start looking at some applications. Thanks for listening, of course, everybody.